In the last lecture, we have introduced the concept of equivalent norm, which is defined we say the two norms are said to be equivalent. The norm this and norm 0, they are said to be equivalent if there exists the number, real number a and b, such that this condition holds good for all x belonging to the norm space x. And we have also discussed about an example where all the norms defined over R2 in a very different way, they are equivalent norm basically. In fact, we have in general the result which says that for a finite dimensional case, on a finite dimensional vector space, any norm is equivalent to any other norm. So, on a finite dimensional vector space X, any norm, that is norm of this, is equivalent to any other norm, that is norm of 0 defined on it. So, this is general results. Since R2 is a finite dimensional case, so that is why we are getting with the in example, in the previous example, the norm which we have defined in the form of norm x1, norm x2, norm x infinity, they are coming to be equivalent norms. So, let us see the proof of this. Suppose the dimension of the vector space X is n, and let E1, E2, En be the basis elements for this. We basis for the vector space X. So, any element of this, so X if any arbitrary element, it can be expressed in terms of the basis element expressed as a linear combination of the basis element alpha x1, alpha 1 x1, alpha 2 x2 plus alpha n xn. Now, if we take the norm of this with respect to the first one, then what we get is norm of alpha 1 x1 plus alpha 2 x2 plus alpha n xn, or this is equivalent to sigma norm of this, sigma alpha I xi, I is 1 to n under the norm. Now, since x1, x2, xn, these are the linearly independent vectors, because they are the elements of I am writing E1, E2. So, let it be E1, E2 here, E1, E2, En. So, here is En, and this is also E1, E2, En, and since E1, E2, En, these are the linearly independent vectors, because they are the basis elements for X. So, according to that one lemma which we have proved earlier, that in case of a linearly independent vector, one cannot get or we cannot expect a vector involving large number of scalars with a minimum length. So, we can always get a constant c greater than 0, such that this norm x greater than equal to c times sigma mod alpha I is 1 to n by lemma, which we have shown earlier. Clear? So, from here we can get this part, norm sigma of mod alpha I is 1 to n is less than equal to 1 by c norm of x. Let it be 1. Okay. Then again we start with this norm x under 0, the norm x, the value of x under the norm 0. So, this will be equal to norm alpha 1 x 1, alpha 1 e 1, alpha 2 e 2, and then alpha n e n with 0. Apply the triangular inequality. So, we are getting is less than equal to mod alpha 1 norm e 1 0, mod alpha 2 norm e 2 0, and so on mod alpha n norm of e n 0. If I take k to be the maximum of say norm e I 0, I is 1 to n, then this whole thing can be written as less than equal to k times sigma I is 1 to n mod alpha I. But we already have it from this equation 1, sigma of alpha is less than equal to 1 by c into this. So, we can further write it, this is less than equal to k into 1 by c norm of x, and that gives you the norm of x 0 is less than equal to say beta times norm of x, say this, where beta is some constant greater than 0, some constant beta. Okay. Now, if I interchange the position of norm 0 and norm, then we get in a similar way norm of x is less than equal to alpha times norm of x 0. So, combine a and b, we get a constant a and b can be obtained such that norm x lies between norm x 0 is lying between a times norm x less than equal to b times norm x. So, this is the result which we require to. Okay. So, any two norms one can on a finite dimensional space are equivalent norms. The advantage of this result is that in case of a finite dimensional space, we need not to bother about the kinds of the norm, because they give the same topology. Topology generated by any norm, whether it is norm 0 or norm x, will be the same. What is the topology in fact? The topology means like a topological space this is a pair x tau, where x is an arbitrary set of elements. X is an arbitrary set of elements, and tau is the collection of all the subsets of, and tau is the collection of subsets of x, which satisfies the following property, which satisfy the following property. The first property that we get tau 1, the empty set phi and x both should be the element of tau, must be an element of tau. Okay. Second property is that the union of any members of tau is a member of tau, is a member of tau. Any union of any member of tau is a member of tau. And third property, the intersection of finitely many members of tau is a member of tau. So, if these three properties are satisfied, then we say the pair x tau is a topological space. In fact, if I go a general result, suppose x be a any arbitrary set and tau is the collection of open subsets of x, then obviously empty set is an open set, x is also an open set, because these are the two non trivial cases, and then the union of any collection of the open set is again a open, the finite intersection of open set is open, which is well known results. So, this set x with tau will be a topological space. Clear? So, collection of all the open subsets of x will form this. In fact, this is the, from here we have generated these definitions, and because since this is true for all so we can take this definition as an axioms or for the topological space or definition. Now, in case of the metric space, if x d be a metric space, then our distance notion dx by that also gives you the topology, because you take any ball around the point this, find out the 2 point or say x naught, you can always find the distance between x to x naught by using this formula. So, an open ball means if the collection of all such point whose distance we can draw the ball which is totally contained inside it, such thing we can always find. So, this x t which is a metric space is a particular case of topological space. In fact, every metric space is a topological space. Is satisfied. What we are interested in, this equivalent norm, when you take the equivalent concept of the equivalent norms, then this equivalent norms give the same topology. That is, the corresponding metric space when we get it, you are getting the collection of open set will be the same. So, that is the concept. We will not go in detail about this topological space, because it is another part of the here we called it the topology for it. Okay. Now, we come for now our concept of the compact set. What is the compact sets? A compact set or compactness in a metric compactness in a norm space. We define a metric space X is said to be compact if every sequence in X has a convergent subsequence. This we also call it a sequentially compact set. Definition of the sequentially compactness. In fact, there are three ways of defining the compactness in a general topological space that requires the concept of the open cover. Every open cover has a finite subcover, then the set will be a compact set. Then every countable cover has a finite subcover, then it is also a compact set. And third is the sequentially compactness. The cover be mean, suppose X be a set and this is our set M. There exist the subsets of X, say B alpha, which is a subset of X, such that countable union of B alpha covers M. Then we say this collection of B alpha is the cover of M. And when this collection only finite number of B alphas are required, then we say it only finite number of elements are sufficient to cover M. Then we say this collection, this cover has a finite subcover. So, we define a set M in a general topological space as a compact set if every cover has a finite subcover. Okay? The open cover has a finite subcover. Then if they are countable in number, then every countable cover has a finite subcover, then also we say it is a compact set. And third one is if every sequence in M has a convergence shape sequence which converges to a point in M, then we say it is a compact set. So, in case of a metric space, all these three definitions coincide. Therefore, we can pick up any definition of a compact set either in the form of cover or maybe in the form of sequence. This is the most convenient way of defining the compactness in terms of the sequences. So, that is why we have chosen a definition of a compact set in a metric space H. A set is compact, a space is compact if every sequence has a convergent subsequence. Now, if M is a subset of M, then M, how to define the compactness of M? This we say that a subset of M, a subset M of X is said to be compact if M is compact, considered as a subspace of X, as a subspace of X. It means the meaning of this is that every sequence in M must have a subsequence which converges to a point of M. That is, the meaning is every sequence in M, has a convergent subsequence whose limit point is an element of M. Okay. So, if a sequence whose limit point may not belongs to M, then M will not be considered to be a compact subset of M. Okay. So, condition for the compactness for a subset is that all these points of the sequence must be the point of M, and when you take the limiting value, the limit point has to be the point of M. That is the definition. Okay. Now, we have a very simple concept in the of a compact set in a finite dimensional case. In fact, we will prove that in case of the finite dimensional, a compact set means it is closed and bounded. That is, every closed and bounded set is compact and vice versa. But in general, when the space is not finite dimensional, then this concept, this closed and bounded set need not turn out to be a compact set. So, that we will see. Before going, let us see the one lemma that shows the one way in a general metric space, a compact subset M of a metric space X D is closed and bounded, So, this is the result true for any arbitrary metric space, whether it is a finite dimensional or whether it is a infinite dimensional. A compact subset of a metric space will always be closed and bounded. The proof is like this. We want M to be closed. M is closed. This is required to prove. Okay. So, that is what to prove is M bar is equal to M, but M is always be a subset of M bar. So, it is enough to prove, enough to show M bar is contained in M. So, finally, if I prove that M bar is contained subset of M, then M will be closed. So, let us take an element X belongs to M bar. What is M bar? M bar is the closure of, this is the closure of M, that is a set which contains all the points of M together with its limit point. So, if X belongs to M bar, either X will be a point of M, then nothing to prove because it will be a subset of M. But if X is not a point of M, then it has to be a limit point of M. So, this implies that there must be a sequence x n in M such that x n must go to X in the of course metric D, whatever the metric D is there. So, there is a sequence which converges to X, but what is given is M is compact. So, every sequence must have a convergence subsequence. So, this sequence will have a convergence subsequence, but since M is compact is given. So, by definition every sequence has a convergence subsequence. So, x n will also have a convergence subsequence whose limit point will not different from x, because the limit point will remain the same. So, that way if x n is a convergent, all of its subsequence will have converge to the same points. So, it has a convergence, therefore, this sequence x n has a convergence subsequence which converges to X, and it must be a point of M because M is compact. Therefore, M bar is a subset of M. So, M is equal to M bar, hence M is closed. Okay. So, if M is a compact set, then it has to be a closed set. To show the M is bounded, this we will prove by a contradiction. Suppose it is not true. Suppose M is unbounded. Suppose M is not bounded. It means the meaning is this, that a set is said to be bounded if this is set M. When we say it is bounded, if we are able to draw a ball around a some point B with a positive radius r such that all the points of the set M are totally within this ball M, is it not? So, if we assume M is unbounded, it means there must be a some sequence of the point in M available whose distance from B keeps on increasing as n tends to infinity, means we cannot find any suitable radius r, so that a ball can be drawn around the point B with a suitable r such that all the points are inside the ball. Okay. So, if M is not bounded, it means there exists a sequence by n in M such that the distance of by n from some fixed point B is greater than n, okay, where V is a fixed point, n is some fixed point of M. So, as increases, y distance keeps on increasing. Therefore, this by n, this sequence by n cannot have a convergence subsequence, because if it is has a convergence subsequence, its distance from B cannot be an arbitrary large. It will always converge to a certain point and distance will remain less than a finite number. So, this shows this sequence by n cannot have a convergence subsequence, which will contradict our assumption that M is compact, because M is given to be compact. So, which contradicts the fact that M is compact, because by definition a set is said to be compact if every sequence must have a convergent subsequence. Therefore, our assumption is wrong. The assumption is that M is unbounded is not correct. Therefore, M is bounded. So, M is bounded. Clear? So, this lemma suggests that if a set is given in a metric space and if it is given to be compact, then it has to be closed and bounded. But it does not say anything about the converse side. If M is given to be closed and bounded in an arbitrary metric space, whether this set M will be compact or not. Now, in general, this is not true. So, converse is not true in general. That is, a set, a closed and bounded set in a general metric space, in fact infinite dimensional metric space X D need not be compact. For example, suppose I take this set M or X to be L infinity, set of all bounded sequences, and M be the set of this type 1 0 0, E 2 0 1 0 0 and so on, E n 0 0 1 0 0, like this. It is nth place and like this. Suppose M is this set. Now, the norm of this is defined in terms of the supremum over I. So, each one is having the norm 1. And so on. Each has the norm. It means the set M. So, the set M is bounded set. Clear? The M is also closed. Why? Closed means all of its limit point must belong to it, but basically the set M is a point set. Since M is a point set, point set means each one is a point only. So, they do not have any limit point. So, no limit point is there, no limit point. It means we can assume all the limit point lies inside this. So, M is closed, but M is not compact. Why? Because if it is compact, then by definition every sequence must have a convergent subsequence. Suppose I take a sequence like E1, E5, E9 and so on. What is the limit point of this, or whether this will have any subsequent limit point lies? No, because E1 is 1 0 0, E5 is 0 0 0, 1 and 0 and like this. So, there is no relation between this and cannot, it means it cannot go to any limit point. Okay. So, a sequence cannot have we cannot get a sequence which has a convergent subsequence. Therefore, this example shows that M is not compact. So, though it is closed and bounded, but it is not compact. What is the dimension of L infinity? It is infinity. So, here we have chosen an example where the space is L infinity and we have got a thing where M is closed and bounded, but not compact. So, in fact, we will have a result. That result says that in case of the finite dimensional space, the closed and bounded sets are compact. So, that is very good results, that for a finite dimensional case the closed and bounded sets are compact. So, in a finite dimensional case, in a finite dimensional norm space X norm, any subset M of X is compact if and only if it is closed and bounded Okay. So, we have already seen the one way that if M is compact, then it implies closed and boundedness. Every compact set is a closed and bounded, whether the space is finite dimensional or infinite dimensional. The other way around was a problem, because in case of the infinite dimensional, we have seen the closed and boundedness space need not imply the compactness. But here in case of the finite dimensional, we will prove that even the closed and bounded set will also lead to the set to be a compact set. So, suppose M is closed and bounded. Okay, this is given. Let it not suppose, let M be is closed and bounded, or given that M is closed and bounded. Clear? We wanted to prove M is compact. M is compact. It means if I prove that every sequence in M has a convergent subsequence, then it will be compact. Okay? So, let X M be a sequence, be an arbitrary sequence in M. Now, since the dimension of X is n, which is finite, and let E1, E2, En, these are the basis element for X. So, X M can be expressed in terms of these basis element as alpha 1 E 1 plus alpha 2 M E 2 plus alpha n M E n. Means there exist scalar alpha 1 M, alpha 2 M, alpha n M. So, that X M can be expressed in terms of this. Clear? Now, given that M is bounded, so norm of X M must be bounded by certain number k. K is greater than equal to norm of X M. Okay, because norm of X M is less than equal to k, the length will be finite. But what is the norm? This is equal to alpha 1 M E 1, alpha 2 M E 2, alpha n M E n. Now, again E 1 E 2 E n are linearly independent vectors. So, by that lemma again, that one cannot expect a vector involving large number of scalars and the minimum length. It means there will be a constant C such that this thing will hold. Where C is greater than 0. Okay. So, from here we get that sigma of alpha I mod alpha I M I is 1 to n is less than equal to k by C. Let it be 1. Okay. Let it be 1. Now, if I fixed I, then this alpha I M mod of this is bounded sequence. So, this sequence alpha I M is a bounded sequence. So, if it is a bounded sequence, then by Bolzano-Weierstrass property. So, by Bolzano-Weierstrass theorem, every bounded sequence has a convergent subsequence, or it has a convergent subsequence. So, by Bolzano-Weierstrass property, it has a convergent subsequence, is it not, which converges to a certain point, say xi alpha I m is a convergent subsequence. Therefore, our sequence x m has a convergent subsequence, say z m, which goes to the point z, which is equal to sigma alpha I e I 1 to n elements in this class belongs to M. Okay? Why belongs to M? Which belongs to M because M is giving to be closed. Because we have assumed M is closed and bounded. So, boundedness, from the boundedness we have got this part, that since because the boundedness for each fixed I, this sequence of scalars is a bounded sequence. Once it is bounded sequence, apply the Bolzano-Weierstrass property theorem, you will get a subsequence which converges to alpha I. It means alpha 1 m will converge to alpha 1, alpha 2 m will converge to alpha 2, and so on. So, the point x m has a convergence subsequence which converges to alpha 1 even, alpha 2 is alpha n. Now, this point A must be a point of M because M is given to be closed. So, any sequence whose limit point, all the limit point must be the point of M. Therefore, this belongs to M. So, what we conclude is that if we start with an arbitrary sequence in M, then it has a convergence subsequence whose limit point belongs to M. Therefore, M is compact. So, this completes the proof. Clear? So, in a finite dimensional case, the compactness is nothing but the closed bound, and that is why in case of the R 1, in case of the C 1, we simply say closed and bounded sets are compact, okay, like this way. Clear? We get. Okay. Now, there is another results which will give you a further deeper study, which will help you in further deeper study of the norm space for in case of the finite dimensional. The result is known as F-Rh lemma. F-Rh lemma. What is this lemma? The lemma says let y and z y and z be subspaces of a norm space of a norm space X, subspace of a norm space X of any dimension, and suppose that Y is closed and is a proper subset of Z. Then this lemma says, then for every real number theta, in the interval 0 1, there exists a Z, or there is a Z belonging to capital Z such that the norm of Z or length of this vector is 1 and its distance from the element Y is our pre-assigned number theta for all y belonging to capital Y. So, it is very interesting. What this shows is that suppose here we have a norm space, okay, X norm, and let this be a Y and this is our say Z. Both are subspaces of X, but Y is given to be a closed and proper subset subspace of subset of Z, closed as well as proper. Then what this shows is that if I take any number theta between 0 and 1, say 1 by 4 or 1 by 2, then corresponding to that number one can identify a point Z in capital Z whose length is 1 and whose distance from any elements y, distance of this from y is greater than equal to theta, where y belongs to this, because Z minus y is greater than equal to theta. Okay. So, this will be a lemma and which will help you in computing in proving many results in case of the finite. The proof of this lemma goes like this. Since y is a proper subset of Z, so let us choose an element V belonging to Z minus y. Okay. So, V will be another point here. Since y is closed, so find out the distance from B to this y. So, let A be the distance of V from y, that is by formula the A becomes infimum of norm V minus y over y belongs to capital Y. Okay. Now, obviously, A is greater than 0 because y is closed. So, we can always find a point, we can get the point whatever the V, it lies in y only and V is lying outside of the V. So, the A must be greater than 0. So, clearly A is greater than 0 as y is closed. Okay. Now, let us pick up the theta, choose theta belonging to 0 1. Now, this infimum definition says that since the infimum is attained, so we can find a point y naught in this where the infimum is attained, and that y naught v minus y naught is exactly A. So, if we take any point other than y naught, then what we get is we can find out the number between A and A theta y, A and A y theta, A and A y theta, theta lying between 0 1. So, A y theta is greater than A and this infimum is attained. So, we can find out the there is a point y naught such that infimum that this is greater than equal to norm of V minus y naught is less than equal to this, okay, because of the infimum thus one. Okay. Let us choose Z as C into V minus y naught, where C is C not Z, C is 1 by norm of V minus y naught. Suppose I take Z this. By choosing this way, we can immediately say mod Z is 1. Okay. And what is its distance? From any arbitrary point y, that comes out to be for any y belongs to capital Y, we have norm of this thing y, which is equal to what? Norm of C V minus y naught minus y, and this will be equal to C, if you take it outside, V minus y naught minus C inverse y, which is equal to C V minus y 1, because where y 1 stands for y naught plus C inverse y, which is an element of y, because y is a subspace. So, this will be the point in y. Okay. Now, this C is nothing but this one. Okay. So, which shows that y 1 belongs. Now, v minus y 1 is greater than a. This is greater than equal to c into a. Why? Because y 1 is an arbitrary point and a is the minimum infimum. So, this substitute this, c is 1 upon into a, and this part is greater than equal to what? A by theta, okay, because of this, clear. So, from here we get this is equal to theta. So, since y is an arbitrary point, of capital Y. So, we get for any point z minus y is greater than equal to theta, and that is the required complete proof. Okay. This lemma, Rh lemma, gives you immediate one application of this, that in case of the finite dimensional, if a norm space has a property that a unit wall is compact, then it must be a finite dimension. So, if a norm space X has a property, this result application of this lemma is, if a norm space X norm has a property that the closed unit wall M norm of X is less than equal to 1, is compact, then X is finite dimensional space. So, this is a very interesting and important result, because so far we have seen a if X be a finite dimensional space, then a closed and compact bounded set is a compact set, because closed unit wall is a bounded and closed. So, it must be compact, but if I take the other way around, if a norm space has a property that a closed unit wall is compact, then it must be a finite dimensional. So, let us see the proof of this. Again we prove by contradiction. Suppose M is compact, given M is, assume that M is compact, but X dimension of X is not finite, is infinite. So, when say the dimension is infinite, then we can find out the so many points inside it, x 1, x 2, x n and so on. So, let us pick up a point x 1 of norm 1. So, let x 1 belongs to X such that norm of x 1 is 1. Now, with the help of this x 1, generate a space x 1. Generate x 1 as a linear combination of this, which is a subspace of X of dimension 1. Now, this is a proper subset of X. This is a proper subspace of X. So, by this previous lemma, by Rh lemma, we can find a point x 2, which is in X having the norm 1 and whose distance from x 1 can be made greater than equal to theta. So, we can, so by Rh represent Rh theorem or lemma, we can, there exists an element x 2 belonging to X of norm 1 such that the distance from x 2 minus x 1 is greater than equal to theta, say half. Okay, say half. Now, we have got the 2 points x 1 and x 2. So, generate with the help of these 2 points another space x 2, which is the linear combination of alpha x 1 plus beta x 2, linear combination of this, okay, generates this one, all alpha beta are constants. So, it is a span of x 1 comma x 2. Now, this is a subset of x again and again a proper subspace of x. So, again by Rh lemma we can further find. So, by Rh lemma or Rh theorem we can find x 3 in x of norm 1 and of norm 1 such that his distance from the elements of x 2 will be greater than equal to the value theta, say half. Greater than equal to half. So, if we continue this way, we get a sequence norm of x 1 x m minus continue this way, we get this is greater than equal to half for n and m as large, for any n m greater than equal to certain points. Okay. What does shows? This shows that this sequence x n, the sequence x n cannot have a convergent subsequence, have convergent subsequence. Why? Because if a sequence is convergent, it must be a Cauchy sequence, because it is a sequence of real or complex number. So, if it is a convergent sequence, it has to every Cauchy sequence, it is a Cauchy sequence. Convergent means it is Cauchy. So, distance between x m minus x n must be less than epsilon. But here the distance between x m and x n is greater than equal to half, arbitrary say greater than equal to say epsilon which is greater than which is equal to half. Therefore, this sequence cannot have a convergent subsequence. Hence, if it cannot be convergent subsequence, hence the set M is not compact. So, this contradicts the compactness of M. This contradicts the compactness of M. Hence, our assumption, that is the x has a dimension infinity, is wrong, that is dimension of x is fine. So, the dimension of x must be finite, that is what exactly we prove. Okay. So, this compactness is now there are certain problems which we will discuss here. Now, R n and C n, these are the compacts or not. Let us see few problems here. Okay. As we have discussed last time, there were some examples for the norm on a metric space, norm on the matrix, norm on matrix. Okay. Let us see just one or two. Suppose A be a matrix A I j of order m cross n with fixed m, and the A I j may be either real or complex. Okay. Then we can introduce the norm in so many. The norm of this A can be written as sigma like this A I j and then this way A I j mod A I j, summation is suppose I is 1 to n 1 to m, and then maximum value you can choose over j. You verify whether this is a norm, verify whether this norm. Another way is I am just saying norm 1 is the maximum of I sigma j 1 to n A I j, whether it is norm, and then you can also define in another way. Okay. So, first you verify these are the norms and whether they are equivalent norm or not, that will give from the okay. Thank you. Thanks.